Hi guys, this is Math 1500. I'm going to cover the central limit theorem for sample means, and we also refer to this as sampling distribution. Let me explain the reason I'm doing this. This is for the most part the lecture that I gave in class on Thursday night, and Thursday night in our area was when trick or treat was, and as the father of two 10-year-olds, I realized that you don't need to be missing Halloween when you have kids of that age group. And I know that some of you missed, and I completely understand why you did. Responsibilities to your family are important, just like they are to me. So what I decided to do to accommodate those of you that were forced to miss on Thursday night, and to really to accommodate those of you who were able to make the lecture but just would like to see it a second time, third time, fourth time, whatever it may be. This is the reason that I'm putting this up. What I want you to do to begin the lecture is, first of all, you may want to pause me, and I want you to go to my stat lab. And again, it's not unlike a presentation in class. You can't just hit pause, but you can here. But in the meantime, if you go to my stat lab course, under document sharing, you will see a link, a document, or well, I should say a link to a document that I just uploaded. So if you'll click that, what's going to happen is you're going to get a Word document. So if I click this one time, you're going to see this document here. Now this is exactly the document that I submitted in class on Thursday. Okay, so what I want to do first of all is I want to tell you what this central limit theorem is all about. And then we're going to work these problems, which are going to be really, really helpful when you go to work this week's homework assignment. So hopefully you're up to snuff and you know what I'm trying to accomplish here. Okay, so again, hope you enjoy. It should probably take I don't know how long it'll take. Actually, probably I'm thinking we're probably going to be done in about 40 minutes. So let's see what happens. As I've told you, the rest of the class, after we get through descriptive statistics, looks at the relationship between samples and populations. And really the way we interpret this relationship is all about the direction that we start and we're headed. If we look at the bottom, for example, where I've drawn this line in this direction, we refer to this direction as probability. Guys, trust me, I can spell probability, I just don't know if I can write it. In this direction, the population value is known and the sample is unknown. So a situation like this is we have a standard deck of cards, 52 cards, 4 suits, faces, kings, queens, and so on and so forth. We know the deck of cards, the distribution that we start out with. Now we can determine the probability of getting an event or a sample from the population using laws of probability. But when we choose this sample, what we get is unknown. Now an example that I used in class the other night is, let's say that I'm driving home tonight and I stop at the local BP in Vanceburg and I play the lottery and I win $15 million. Well, first and foremost, you guys are going to be getting a new statistics professor, but as much as I love Shawnee State University, I would want to definitely give back to the place. So what I would probably want to do is I'd want to create some scholarship funds. So let's just say hypothetically that I won the lottery and I decided that I wanted to choose one person, one student from Shawnee State University to get the scholarship. Well, guys, clearly my population would be all the students who are currently enrolled in Shawnee State University. And from the registrar's office, I could get a list of all those names. So I would know all of the names that I'm choosing from. But if this thing is truly chosen at random, this person, this name is truly chosen at random, In random, a good way to think of that is you just close your eyes, you go in and you pick one, at random. Probability would tell me the likelihood of getting, a particular name. This is unknown because if it's truly random, I don't know which student that I would select. Now the other direction is called inference. And in my opinion, and the opinion of most people, this is the most important branch of statistics. And in this branch of statistics, everything kind of flips from the probability perspective. For example, the population is now unknown. I should say the population value. And the sample becomes known. Now, I live in the state of Kentucky, and at the current time that I'm putting up this this video, we are getting a lot of attention on a Senate race, which is coming up soon. A lot of people want to know what percentage of Kentuckians are going to vote for a particular candidate. And let's just go with McConnell. He's probably the best known because he's been in Washington, D.C. for, I think, over 30 years. Well, people that do this for a living that want to try to determine that have to understand that the percentage of people in Kentucky that are going to vote for this particular candidate is unknown. So what they'll do is they'll go out and get a sample of maybe, who knows, 500, 1,000 Kentuckians and ask them if they intend to vote, and they'll evaluate their sample. At the end of evaluating their sample, they will know how many people that out of the total that they surveyed intend to vote for Senator McConnell or Grimes, who is the opponent. But even though they know for that small segment, that sample, it still doesn't tell us the percentage of the entire population that intend to vote for that particular candidate. But as we'll find out later in the class, we can use this information and some statistical maturity, if you will, to get a pretty good estimate if it's truly a random sample. So guys, the focus of what we're going to do now kind of switches from proportion to probability. So we want to be able to switch our attention from proportion to probability. And you know what? It turns out it's really easy, kind of cool, because of the definition of probability. If you go to your textbook, the definition of probability is the following. It says probability is the proportion of times an event occurs over a long sequence of trials. Now, the first part of that definition that I want to tap into is long sequence of trials. Why do we have that? Well, if you pull out a coin out of your pocket and you flip it one time, well, we all know that if it's a fair coin that the probability is 0.5 that the coin lands on a tail, for example. But that doesn't necessarily indicate that when we flip that coin 10 times that we will always get 5 heads and 5 tails. In fact, we know there's going to be natural variability there. And out of every 10 times that we flip the coin, we're not necessarily going to get 5 heads and 5 tails. We may get 2 heads and 8 tails. Yeah, I guess it's actually possible that we get no heads and all 10 tails. That'd be low. The probability that would be very low. Okay, so but if we think about the long sequence part here, if we sit there and flip that coin 1,000,000 times, we'd be bored to tears. But we would expect over a long series sequence of trials to get about 50% heads and 50% tails. Now, the next thing I want you to notice is the probability is defined in terms of something you already know how to do. And it doesn't get much better in mathematics when you get a definition that is presented to you in terms of something you already know how to do. For example, if I tell you the problem IQs form a normal distribution with a mean of 100, standard deviation 15, and I ask you what proportion of IQs are greater than 125, thinking through the things I've already taught you in this semester, you're asked to find something starts with a P. You're going to think P key. And we should all be able to work this, well, obviously I can, but all of us in the class should be able to work this example by entering this information into our calculator. Now, I'm not going to get the answer because, again, the process is more important to me right now than the final answer. Well, let's go back to what if we were asked the following question. A person is selected at random. What is the probability there's an I there, guys. Their IQ is greater than, what did I say, 125, yeah. Well, new type of problem, right? We're looking at the probability instead of the proportion, but we can go back to the definition of probability, and probability is simply the proportion of times something happens. Well, guys, that's super cool because we can use that to work this problem, and guys, it turns out that this problem would be worked exactly like the proportion problem. So asking what proportion of IQs are greater than 125 is equivalent to saying a person is selected at random, what's the probability their IQ is greater than 125? I got to tell you, we're running a little bit behind in this class. I would say we're probably a class behind. And I've got to cut out a couple of things. And probability is really, really cool stuff. I think my addiction to Las Vegas is partly fueled by my interest in probability. But we have people at the university, Dr. Lee and Dr. Whitaker, who are experts in this field and much, 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 much better at teaching that than me. My job is to teach you statistics, but we look at probability because it plays such an important role in inference. Now, so anyway, highly recommend taking a class in probability. It would be really cool stuff. But this class is in statistics, so we'll keep on task. Now, what I want you to think about is this statement right here: a person. Now, guys, when you see that, you should think, well, n is equal to 1, right? Now, if we go back to the beginning of the lecture, so to speak, I told you that the rest of the class, after we finish the descriptive statistic part, deals with the relationship between samples and populations. Everything that we learned down here in terms of probability will play an important role up here in terms of inference. In fact, we can kind of think of this as a vicious cycle. Everything we learn in probability ultimately comes up here to the inference part. So, keeping that in mind, what do you currently know how to do? That's going to bug me, sorry. All right, cool. So what do we know so far? We just found out that a problem like this where one person is selected at random, what's the probability that working that problem is equivalent to the proportion? So we just found out that in terms of probability, when we take one person at random from a population that's given, and in this problem right here, what was given was IQ scores and the mean of 100, standard deviation 15. We select one at random. We don't know what we're going to get. That's where the unknown factor comes. But what we can do with us being able to work problems where the sample size is equal to 1, we are now prepared to conduct inference. Again, if this vicious cycle actually exists, and trust me it does, we are now prepared, we have the tools, if you will, to conduct inference on a sample of 1. Now, if you want to talk about ridiculous statistics, think about conducting a study on one person. Let's go back to the Kentucky election. We'd really like to know the way that the residents of the state of Kentucky are going to vote. So what do? Well, we go out and get a sample of 1, and we ask the person, well, who are you going to vote for? And they say, I think I'm going to vote for Grimes. Well, I guess everybody in Kentucky is going to vote for Grimes. That's dumb stats. That's not what we do. We want to create a sample that has variation in it. So we're going to need more than one person. In fact, we're going to need 2 or more. So because of that, we need to come down here and study what happens with probability when our sample is greater than or equal to 2. Now guys, I'm giving you a very specific example here, and we're just looking at quantitative data where we would summarize our data using a mean. Now if we're using categorical data where we summarize data using frequencies and percentages, what I'm showing you here doesn't work. So this is for quantitative data where we can calculate the sample mean, the sample standard deviation, and where our population is provided in terms of the mean and the standard deviation. A lot of problems at this level of statistics are given as a proportion. What percentage of people believe in ghosts? Well, that's a situation where our population is described by a percentage, and the process that I'm demonstrating to you right now doesn't apply. This is a situation where our population is presented as a quantitative variable, and we have means and standard deviations and so on and so forth, like we've learned so far. So guys, what we need to do is we need to explore, what does this probability look like when we have sample sizes greater than or equal to 2? Well, the answer to all that is called the central limit theorem. And at the end of the day, and you find all sorts of variations in the way this thing is presented, but at the end of the day, the central limit theorem kind of works like this. The first thing we do is we start with a population. And since we're interested in quantitative variable, we start with a population where the mean and the standard deviation are given. Now, things kind of change a little bit depending on the type of distribution that we begin with. But if we start out with the normal model, or where our population is described by a normal model or normal distribution, really our sample size that we need to work with has to be 2 or bigger. Well, we needed that anyway because we're dealing with means, right? We're looking at ultimately what do these means all look like? How do we describe them? And we'll get into that in just a second. Well, if you think about it, you got one person, you just got a score. So you've got to have at least 2 people to get a mean so you can add the scores together and divide, of course, by 2 or more. The next thing for this class I want you to think about is what happens when we have skewed distributions. Now, when we have skewed distributions, we need a larger sample size to make things work. And typically, 25, 30, hopefully 100. If we can get sample sizes around 30, then cool things tend to happen. So we'll only go to the next page if our sample size restriction is met. Okay? So we read a problem. Population, IQs, mean 100, standard deviation 16, or 15, I'm sorry. And we have a normal model. All we need is 2 or more. If this is met, go to the next page. Positively, negatively skewed distribution. Sample size, 25, 30, the bigger sample size is met. Now, the next thing we want to do is we want to let the cool stuff start. And the first thing that we think about in this capacity is we need to set in. Fix it. Don't let it vary. And just for the sake of me speaking through this problem, I want to just say that n is equal to 40. It's not going to be 40. Sometimes it's 5. Sometimes it's 1,000. If you're going to conduct a large-scale study, you might have access to 300, 500, 1,000 people. I've seen data sets that had 12,000, 15,000. But sometimes you have to work with small data sets. Let's just say, for the heck of it, you work for BMW. And they just came out with this new fancy 6 Series car, and that sells for $100 and some thousand. And you'd like to run some of them in a wall just to see if you can find out what the average the crash analysis will look like. So you go to the CEO of BMW and say, you know what, I'd like to have 1,000 of those 6 Series so I can go out here and run them in a tree. You're probably going to lose your job. That's probably not going to work. You may have to take 3 of these things and go out there. So, sample size, I've always heard, get as many as you can get. But, as you might imagine, it's not quite that simple. Because, we'll learn, there's power issues, and, we'll learn stuff like that at the proper time. Now, the next thing you do is once your n is fixed, you think about, my pen just lost its mind. You think about what would the random samples of size 40 look like. So guys, imagine coming back over here to your population that you begin with there, and you randomly select 40 observations. You add those 40 observations up, you divide by 40, and you get your first sample mean of size 40. Now, what is that number? Well, I'm not worried about that number. I'm worried about presenting it more theoretically here, okay? But we've all got to agree that it would be easy to visualize that pulling 40 numbers out of that distribution and being able to add them up and divide by 40 and get the mean. Well, imagine being able to do that again. So put the first 40 numbers back in the population. Pull out another 40 numbers randomly. There could be some replication. Probably not if we have a large population. And we end up getting our second sample mean. Well, let's do that again. And again. And imagine in theory that you could do this forever. Now, that'd be a long homework assignment, wouldn't it? If you sit there and just keep drawing samples out, yeah, it wouldn't be cool because you'd never get out of the class. Kind of reminds me of the song by the Eagles, Hotel California. Well, you check in, you never check out. So you check in to Darbro's stats class and you never check out. Well, trust me, I'm going to get you out of here, or do my best at least anyway. So again, think of this just in theory. So at the end of the day, once you did all this work, and again, you don't do this work, you just kind of realize that there are infinitely many random samples of size 40 that could be taken from this large population, and considering some of the samples would be repeated. So, or I should say some of the means will be repeated. Okay, so we have a bunch of sample means, and we refer to this as the distribution of sample means x bar. Now, at the end of the day, what you've just done is you've created a second population. This population back here, and let's just use something that we're familiar with because we've used the example quite a bit. Let's say we start out with a population called IQs. Well, guys, this population right here is taken one at a time. Bill's IQ is 112, Mary's IQ is 130, Frank's IQ is 98, what Bailey's IQ is, whatever it may be. These are taken one at a time. This is the distribution of all IQs. When we get over here to the random sample part, we create a new population, not of individual scores, but of sample means taken, for this illustration, 40 at a time. Now, I told my class the other night that up to now, you could get away with saying those were both means, and they are. If I put mu on the board and I'm like, okay guys, what is that? And somebody said, well, that's a mean. Well, you're right. And I said, well, what's X bar? Well, that's a mean too. You're right. But guys, we now need, since the stakes are getting a little bit higher and we're getting into big boy, big girl stuff, we need to understand that this notation stands for different types of means. Mu stands for the population mean. X bar stands for the sample mean. Well, that brings us into some kind of cool stuff for the central limit theorem. Central limit theorem tells us three really important things about the distribution of sample means. First of all, it tells us that these X bars back there will be normally distributed. Well, that's kind of cool, because when we know something's normally distributed, we've got all these fancy schmancy calculator keys called normal CDF and normal PDF and inverse norm. And we've got these P norms and Q norms on R that work these types of problems for us. So that's kind of cool. Anytime we start out with a normal distribution, that we're assured we have a normal distribution, that's kind of cool because it makes our problems, in many cases, workable. The next thing it tells us is this. Now guys, I've been teaching statistics a long time, and I'll tell you, students lose their mind when they see that notation, because it's like two means. Well, what this is telling us, of this new population, what is the mean of our sample means? What's the population mean of our sample means? And the central limit theorem tells us that the mean of all the sample means. So if I could take, for example, x1 plus x2 plus x3 plus x4 plus, x bar 1 plus x bar 2 plus x bar 3 plus x bar 4 plus, 1,001, just imagine I could add all these things up. I could take my calculator, put all those numbers in L1, hit one variable stats and get the mean. What would it be? Well, central limit theorem tells us that will be precisely the mean that we started out with in the population where the scores were taken one at a time. The next thing we might be interested in is, well, what would the standard deviation look like? Because guys, once we got a normal distribution, we got to remember normal distributions are defined by two measurements: the measure of center and the measure of spread. And when we have symmetric distributions like the normal distribution, the measure of center is the mean and the measure of spread the standard deviation. Now guys, central limit theorem tells us that the standard deviation of the sample means, so in other words, back here, these numbers, x bar 1, x bar 2, x bar 3, the standard deviation of these things would be equal to the original standard deviation divided by the square root of n. Now, this is a really important measurement to us as we move forward. And it's so important we give it a big old fancy schmancy name called the standard error. You're going to see that quite a bit from here on out. We're eventually going to take the standard error and convert it into something called margin of error. But right now we're going to keep it there. Okay? Now, let's work a problem. So again, ad nauseum, we've seen this, and I'm not obsessed with IQ scores. In fact, I don't really even buy into some of that stuff sometimes. I've taken a lot of IQ tests, more than any human being should, and I've yet to score the same thing. So I know there's not only variation in IQs from person to person, there's IQ variation within person, because I have yet to score the same number. But anyway, IQs are normally distributed, mean of 100, standard deviation 15. And let's say that a random sample of n equal 15 no, I don't want that. That's bad. N equal 8 people is selected. Okay? So a random sample of n equal 8 people is selected. What is the probability their sample mean exceeds 105? Now, as an introductory statistics student, we need keys. When we look at a problem like that, how do we know that this is this new tool that we have for this the central limit theorem? How do we know that this problem is what we need to work? You know, sometimes I'm working in a house and maybe I'll need a Phillips screwdriver, and I'll send my wife down to the shed and I say, well, go get me a Phillips screwdriver, and she'll come back with a straight screwdriver. Well, that's the wrong tool for the job. And you know, it doesn't work in home repair, and it doesn't work in statistics. We need to get the right tool for the job. So typically speaking, when you see a problem that asks you to find probability of a mean, you can almost rest assured that you're going to use the central limit theorem for sample means to work that problem. Now, let's go back and look at what I gave you, okay? Let's go all the way back. So, you know, back here I said, you know, we'll start with the population. Well, we did. His IQ scores. And the mean would be given, and it was. And the standard deviation would be given, and it was. Next thing we have to do is we have to kind of pay attention to the distribution that we're dealing with. And IQ's approximately normal, so we just need a sample size bigger than, greater than or equal to 2. And we got that. So the sample size restriction is satisfied. So I say right down here, go to the next page if the sample size restriction is met, which it is. So we go to the next page and we set in. In my illustration, I chose 40. But this problem wants us to focus on 8. Now, first sample mean, I could pull out 8 people, give them an IQ test, add up their IQ, divide by 8, and I get the first sample mean. Another sample mean, or I'm sorry, another sample size 8, add up their IQs, divide by 8, on and on and on. Well, what I call these things, even though I don't calculate them, I know that they exist in theory. What would I call them? Distribution of sample means for size 8. Next thing kicks in, don't forget the difference. Next thing kicks in, central limit theorem. Central limit theorem says these things are going to be normally distributed, which is cool as can be. Because we know now we can work those types of problems with the normal CDF. And guys, forever and always, normal CDF problems are going to require you to put in 4 things. The mean, standard deviation, lower bound, upper bound. All right, so we go back to our problem, and the first 2 things we put in normal CDF, we get from our problem. We got it before from our problem. We're going to get it now from our problem. So exceeds 105. That means 105 and higher. The next thing we do is we need our mean and our standard deviation. Well, the standard deviation tells us, standard deviation. The central limit theorem tells us what those values are going to be. Well, it says the mean of the sample means is going to be precisely the mean of the distribution that we started with. Well, that's 100. So we can go back over here to our calculator key and put 100. But we need a standard deviation, don't we? Well, central limit theorem says that the standard deviation is going to be the standard error is going to be the standard deviation divided by the square root of n. So I go over here. And do the square root of 8. So really, guys, when you guys walked into my class on Thursday night, the thing you already know how to do with normal distributions, the only thing that really changes in this new direction that we're taking with the central limit theorem is the standard deviation changes to the standard error. So if you can wrap your mind around that difference, well, life is pretty good. Okay, well, I don't know if it's good or not, but statistics at least might make a little bit of sense. So guys, what I would recommend now is let's, we're going to find these probabilities either with calculus or your calculator. Yeah, I think I'd highly recommend the calculator. So let's go second function. Distribution, number 2. And our lower bound is 105. Our upper bound is E99, which is infinity. You know, no one has an IQ of 1.2 trillion, but we let the modelers worry about that. Our mean is 100. And our standard deviation is, and guys, it's going to be so tempting to put 15 and go on and do it. Don't allow yourself to do that. Remember, these new types of problems, my processor and my computer's a little slow. I got so much running. So I want the 15 divided by the square root of 8. All right, boys and girls, hit enter. Hit enter again. Hit enter again. And our probability is 0.1729. Alright, this is a little annoying, but we'll work it out. The spinning wheel, don't you love it? So guys, our answer to this was 0.1729. So there's about an 18 out of 100 chance that you would select 8 people at random and their average IQ be 105 or higher. So yeah, reasonable probability. It's just, I guess, how you determine probability, right? A lot of people are, are afraid to fly. I think the Ebola, the people freaking out about that, and trust me, I have my concerns about it, like any reasonable person I think should. But it's funny how I see people. I saw a guy the other day driving down the road, driving with his knees and texting. And I bet you anything, this guy's scared to death he's going to get Ebola. And I'm like, dude, if you want to assess risk, well, anyway. All right. Plus he was eating a big old double cheeseburger and taking in all those ugly. No, he really wasn't. He was just driving and texting, but whatever. All right, gang. I want to work some problems for you. And I'll tell you what I'm going to do. I'm going to shut down the blackboard just to try to save a little memory. Maybe. So what I want to do is I want to go to this this handout, and I want to tell you one thing. I want to change one thing. I've made a typo down here. So down here in number 2, I want you to change that from 25 parties to 40 parties. The reason being, if 25, we really don't have a sample size above 30. We could get a good estimate, but let's go ahead and keep it